So I'm going to be talking to all of you about Project PANOPTES. Oops, it might cut out. Oh, there it goes. I just need to get a little closer. We're going to be talking about Project PANOPTES, which is an open source. Oh, let me try a little lower. There we go. So we're going to be talking about, maybe I'll switch to a hand mic. Or I can try holding it. Okay, we'll see if it works for a while. Project PANOPTES is an open source astronomy project, also focused on citizen science and all that kind of good stuff. And it's also a way that all of you can help us as humans. We can all discover new worlds together. But first, before I get into that stuff, I think we can all agree on something. You're kind of self-selected by coming here. I think we can all agree that space is cool. Yay! Yeah, space and astronomy are a pretty cool thing. And I've thought about this like all my life. I was one of those weird kids that like watched Nova after Sesame Street and didn't realize it wasn't children's programming. And then I like convinced my father to read me from a cosmology textbook instead of like bedtime stories. Yeah, I was that weird kid. And there's good reason for that. A lot of stuff was just around about space at the time. Because growing up, a lot of stuff was still in the kind of the collective consciousness of the adults around me.
It sounds like the audio's coming from a different.
It was an amazing time for space exploration. Things like the lunar landing, the manned missions to the moon, were still pretty fresh in people's minds, the minds of the teachers around me and the minds of my parents. And it had just been really recent that we had seen the first pictures of the surface of other planets. Like this is from the Viking 1 lander in 1976, sorry. And this is a picture from the surface of Mars, and that's really, really, really cool. And these really cool things kept happening throughout my childhood and influenced me. Like this is a picture some of you might recognize. The important thing is to ignore the colored streaks. They're not the important part. That's glare, because the camera's looking kind of close to the sun. There's a little tiny dot in this picture that you can probably barely make out on the projected screen. And if any of you were around Earth in February of 1991, this is a picture of all of us. This is the Voyager spacecraft. Towards the end of the life of its cameras, they turned it around and they took a picture of Earth as well as the other planets. So it's kind of like an old school selfie. I guess if we had really long arms holding the Voyager spacecraft. And the exciting news just kept on coming. And this one even kind of got me into some trouble because my bedtime stories were like astronomy, news, and cosmology textbooks. I was up on the news apparently a little ahead of my teachers. And in school, we were learning about the 9 planets, because there were 9 back then. And I insisted that they were wrong, that there were 10 planets, because we had just discovered another one really far away. And my teacher didn't agree with me or the way I educated my fellow students about it. I got into a little bit of trouble for the insolence. But it was worth it. This planet, by the way, has a wonderful name of PSR B1257 plus 12. It's a cool planet around a pulsar, really far away. And these things are really cool, and they influenced me a lot as I grew up and got me super excited about space and things. But all of these things, from the manned missions to the moon to like this pulsar planet discovery, they all shared one thing in common that was a little bit of a buzzkill. They were all super expensive projects, which means of all the thousands of people involved in like the manned missions to the moon, only a very few people got to go and actually get to walk around. And with a lot of these experiments, you needed to devote your life to get the time on expensive, fancy instruments to be able to do your research. And I like kind of faster satisfaction, the kind of satisfaction we get from web dev and software development today. So my life went in a little bit of a different direction. And I guess I'll introduce myself before I go any further. So these days, I spend my time doing security advocacy at Google, so a different direction than space stuff. But I remained kind of an astronomy geek the whole time. Kind of always kept an eye on the news and all that kind of stuff. And recently, I've had an opportunity, as a regular software engineer type person, to get involved in actual research. And that's what I'm going to be sharing with you today. Specifically, I'm going to break it down this way. Here's our agenda thingy. We're going to spend just a moment talking about exoplanet science and why now is such an exciting time in the field. And then no talk about astronomy, or I guess Spider-Man movie would be complete without an origin story. So we're going to do an origin story of the PANOPTES project to kind of explain why it exists and what's special about it. Then we'll spend a few minutes talking about the hardware that makes it possible, because half of the project is the hardware that's kind of unique to the project. And the other half of the project is the open science experiment, the science we're doing with that hardware. And then hopefully, if I've inspired all of you, the last part will be telling you what we're doing next, which will hopefully involve your contributions, at least some of you. So without further ado, let's do some exoplanet science stuff. So way back in like 1995, as I mentioned, we confirmed the first exoplanet. People had been talking about exoplanets for a long time. They hypothesized they existed. We didn't have a lot of concrete data. And early on, the discovery process was quite slow. But as the years passed, we came up with new clever ways to infer their existence from like very thin amounts of data. And as it turns out, they're kind of everywhere. Like at this point, it's looking pretty likely that there are planets around almost every star out there. Every time there's a star system where it's like, oh, there can never be a planet around a close binary star system like in Star Wars. Like, oh no, we found some. Or like, oh, there can never be planets around a star that's this young or contains this composition of minerals. We actually find those too. So it seems like every time we turn the corner, we find more. And I'm going to talk a little about the different techniques we've used. And there's actually, this is kind of a sample of it, because there's a whole bunch of clever ways people have figured out that either do work for discovering exoplanets or may work in the near future. But these are a few I've picked just to kind of go through to kind of set the stage on the science. So the first is direct observation. Like, why don't we just try and look at them directly? Like we look at stars directly and nebula and other cool things. Why don't we just look at planets around other stars? It kind of seems obvious. Then I'm going to spend some time talking about Doppler spectroscopy, which is the technique that was most productive until about 2012 or so. And then the new technique, which is the one that's super prolific. So every time you see an article where it's like 1,000 new exoplanets discovered, probably by Kepler, which is a space telescope, those were all done using a technique called transit photometry, which is coincidentally the technique that PANOPTES uses. And it's my favorite one. So why don't we just use the obvious technique, which is why don't we try to directly observe? So this is something I did that you should never do. I took my cell phone camera and I pointed it at the sun, and I took a picture. Don't do that if you value your cell phone's camera. It's really bad for it. But this is an old phone, so I didn't care. And like this is our sun. And there's a good chance that there's a planet in this picture that we can't see. Venus or Mercury might be in this photo. But the sun is super bright. And even though we're pretty close relative to exoplanets, we're pretty close to the planets in our solar system, like it's almost impossible to see these under normal circumstances, just because there's too much glare. And it's the same kind of problem, except way worse for planets around other stars. And as a result, we've directly observed a very small number of planets around other stars, because it's very hard. Here's one example of a planet we have observed. This is from Alt B, and this was done using the Hubble Space Telescope, which is above the atmosphere and can get really sharp pictures. And it took several years for us to confirm this. So even if we take like a piece of metal and we block out the star itself to kind of make an artificial eclipse, there's still a whole bunch of glare and other light that kind of gets in the way. Despite that, we did manage to find this planet. It just looks like a little tiny nodule, and that noise is kind of moving along. And today we're at the point where some of the most powerful ground-based telescopes in the world can directly image a very small number of planets in special circumstances. But this is not going to work for finding all of them. This is not going to work for a broad survey. It's just too expensive, and it requires instruments like the Hubble Space Telescope, which is very expensive. So knowing that this technique was probably going to be ineffective, we needed to come up with clever ways to kind of infer that they exist via other signals. And this is where Doppler Spectroscopy, difficult to say, but pretty effective, came into play. And this technique infers the existence of other planets by using rainbows, which is pretty fun. Because it turns out that if you take light from a star and you shine it through a prism or a spectroscope in this case, you get a rainbow out. But those rainbows have a little variation depending on the star. If the star is red, the red parts of the rainbow will be brighter. If the star is blue, the blue parts of the rainbow will be a little brighter. And there's also these notches that show up. And the reasons for these notches showing up is a little bit complicated, and I'm not going to get into it. But the notches are there. And one of the cool things about these little notches is if you reproduce them in a laboratory environment, you get very clean edges, and they stay precisely in the right spot with a very high degree of precision. And we can take advantage of this because in the lab, they seem to stay perfectly still. But for a lot of stars, they kind of wiggle around a very small amount. And by small amount, I mean like a really small amount. I mean like for an individual sample, maybe a thousandth of a pixel on our highest resolution spectroscopes. So very, very small amounts. But we get enough samples, we can add them up, and we can detect this wiggling. And what this wiggling is a Doppler shift, which is a similar experience. Like light is affected by the same thing as if a sound goes past you and you hear the pitch change as it approaches you and goes away. The same thing happens to light. And we use this for all sorts of things in astronomy, but we can also use it to infer those existence of planets. Because stars use gravity to hold their planets in, and they're holding their planet in by tugging it. And although the planet is much smaller than the star, the planet also tugs on the star. So the star will move back and forth a little bit as that planet moves around it. It's actually moving in a circle. But to us, it looks like it's kind of wiggling back and forth because we can't see the side-to-side motion. And the amount of motion we're able to detect is very, very small. We're actually down to the point where we can detect less than a meter per second of motion of a star. So like imagine an unimaginably giant star, and it's moving. We can detect movement that's roughly as fast as I'm walking across the stage right now of that entire object, which is pretty cool. It's a great technique, and it works in a large number of extrasolar systems. But it has a notable downside, which is that it requires very expensive telescopes to look at generally one object at a time and take many samples over a large period of time. So it's expensive, and we have to there's a lot of stars out there to look at one at a time. And that brings us to the third technique I'm going to talk about, transit photometry. And this is the technique that the Kepler Space Telescope used, which is another space telescope that did a survey. It spent a lot of time staring at a chunk of the sky about as big as your hand, and it found a whole bunch of exoplanets using this technique. It could look at several stars in that area all at once. And this technique is all about counting photons. Because when you look at a star, generally, stars have a lot of reasons to vary, but the light from most stars is going to stay relatively constant. That is until something moves between us and the star. So for example, in 2012, in our own solar system, an object moved between us and our sun. This is the planet Venus. And so if you're looking at our own star and our own planet, you can actually see the disk move past it. Other star systems are too far away for that, so the star just looks a little bit dimmer because it's kind of like a point source. It's a single pixel on our camera, and that single pixel gets a tiny amount dimmer. And what's cool about that dimming is it depends on the size of the planet, how close it is to the star, and the size of the star itself, how bright the star is. But in some circumstances, that dimming can be as much as 1 or 2%. So which is a huge signal compared to the other techniques we've used in the past. That is the kind of technique that you might be able to detect using consumer electronics, like the DSLRs you can go buy at the store. And that's where PANOPTES comes in. So around the time people were figuring out that photometry was a useful technique for detecting planets around other stars, and digital cameras were getting really good, there was a group of astronomers down in Hawaii, and they were like, I wonder if this works. And one notable person in that group, Olivier Guillon, the founder of the project, is also a little bit of a hacker, kind of like us. So he did the obvious thing. He dove into his garage and ripped a bunch of stuff out of half-done other projects there, scooped up other stuff that was lying around, and maybe cut up a washing machine, which he won't tell me if it was working before he started or not. He covered it in zip ties and tape and bolted it to the side of his house to see if it would work. And the initial results were pretty promising. Promising enough that he was able to convince an observatory on Mauna Loa in Hawaii to give us some space and convince other people to join the project and help him out. So over the next several years, the prototype got refined. We experimented with things like different numbers of cameras, because the more cameras you have, the more light you have. We experimented with different, do expensive lenses work? Are expensive lenses worth the amount of money? Are cheap lenses best? We refined the controls so that we could do the robotic observations better, the software behind it. And another important part is we were using a device called an equatorial mount, which is what's aiming the camera at the sky. And those operate outside. So we had to go outside to make sure that they function outside. A lot of things, including tape and like rubber seals and that kind of stuff. And after a while, this allowed us to kind of home in on finding out what the sweet spot is on the hardware. And along the way, we got to take some really cool pictures. So while we were experimenting with different exposure settings, it looks like these turned out pretty well on the sides. We found some cool things. Like this one, we took a picture that contained Comet Lovejoy and a Geminid meteor in the same exposure. That was pretty cool. We also got some picture of the Orion Nebula next to the Horsehead Nebula, so I guess it's Orion's belt. And this one's my favorite. We did a really long exposure, and we were pointed at the Virgo Cluster, and it turns out you can make out the shape of galaxies from a photo taken with a consumer SLR, which is something that completely blew me away. So as time passed, we homed in on what is the perfect hardware for this experiment. Because if we can make it cheap, we can hopefully convince people to build more of them and then have a whole lot of them. And that's where the baseline unit design comes in. I think of it as kind of our V1.0 hardware, kind of like, if you think of semantic versioning for robotic observatories. So the goals of our baseline unit were, we wanted something that is based off of 100% commercially available off-the-shelf components. We want you to be able to go to a store, buy all the things you need to build it, and put them together yourself. We wanted the build materials to be roughly $5,000. Seemed to be kind of the sweet spot on the result we were getting. And this worked out well because it allows, it puts it within the realm of educational institutions, which is something we're also passionate about. We want this to be something that not only educational institutions in rich countries can build, but we want this to be something that's within the reach of educational institutions in developing countries and other parts of the world. Because the more places we put these, the better coverage we'll get and the better the science will be. We wanted this to be built with simple tools. So you can actually assemble a PANOPTES baseline unit using only hand tools, and we've done that a couple of times, although a drill press does help a whole lot. And we wanted the skill set required to be something that's within the realm of experience of a high school robotics team, be able to assemble it. Although based on a lot of high school robotics, this would be a cakewalk for them. They're pretty good. And of course, we wanted all the design to be open source. So that someone could take this, and if they don't want to participate in the survey, our primary experiment, they can use it for something else, because that would be cool too. This is part of our baseline unit. This is the meat of it, the thing that does the observing. As it turns out, cheap SLRs work great for this. So we originally used Canon SL1s, which is about the cheapest SLR body you can buy. It's also wonderfully lightweight, being made out of mostly plastic. And now we're using the Canon SL2 because the SL1 got end-of-lifed. And the SL2 is pretty much a drop-in replacement for our purposes. It turns out that cheap lenses are the sweet spot. So we're using some off-brand 85mm prime lenses, which are pretty low cost. And some other commercial off-the-shelf stuff to turn those on and off and copy data off of them. The electronics that make it up include some stuff that people assemble on perf board. There's a single PCB that we ship out to teams that are doing builds for power control. But you could definitely build that off of perf board also. All the electronics components are things like sensors you could get from Adafruit or DF Robot, some relays, capacitors, Arduinos, all through-hole soldering. So this is something that's within the reach of someone doing their first soldering project. And a few other components like an off-the-shelf equatorial mount meant for like consumer astronomical photography, and an Intel NUC to control it all and do some of the pre-processing. And this is what it kind of comes together to look like. So this is the very first prototype getting, I think it's on, this is a 4th or 5th revision, depending on where you decide to count them, going to our first baseline design to test it. We call this particular robot, lovingly call it PAN001, because we're astronomers and we name things like that. And it's performed pretty well up on Mauna Loa. It has definitely gone through the weather testing. It has experienced 140 mile per hour winds, tons of UV exposure. That white case used to be brown. And it's actually been snowed on. And throughout all of that, it's actually been pretty reliable. And this is a pretty big observation because traditionally a lot of these instruments are housed inside domes to protect them, but we didn't want domes because domes are expensive and they're hard to get working and they break all the time. And it worked great. So over the last year or so, we have been expanding our network of robotic telescopes. So we have 3 of them online right now, 1 in Australia, the original one, PAN001 in Hawaii, and then another one outside of Boston up in Massachusetts. We also have 4 more telescopes that are in progress of construction, including one in Arizona that'll be the first one built by a high schooler, which is pretty cool, and mine, which is going slower than the one being built by the high schooler. It's making a little progress. And then we also have like 6 or 7 more teams that are in different stages of acquiring the components with plans to start it at the beginning of the next academic school year. So this fall, we're expecting more to go online in a bunch of different locations, including Italy and Chile. Should be pretty exciting. So that's the robot. Hopefully I've convinced you that it's capable of taking pictures of the sky. But that's only like half of the whole project. The other half is taking those pictures, and from those pictures, figuring out if there are planets around other stars, the science side. And this is kind of how we go about it. So each one of the robotic telescopes has like a hard-coded list of objects that we find interesting that represent kind of the center of the frames we're going to look at. They're the objects we focus on, not the only objects we're observing, but they're kind of, we got to center our frames on something. And thanks to awesome open source libraries, what you can do is you can just list the catalog name of stars, and then if you know like which way north is, I don't know if that's north, and where you are on the planet, you can figure out if those objects are in a good portion of the sky to look at. So when it starts up, when it wakes up at the beginning of the night, it'll go through its list of interesting objects, some of which are in your hemisphere and some of which may not be visible to you ever. It'll find that the first one it can observe that's in a good position, like near the top of the sky where the air mass is low, and it'll look at it for as long as it can. It'll take between 10 and 300 exposures. And the number of exposures depends on your location and how long the exposures are, because you also have to tune the exposures a little bit for the light quality. So if you're in an area with more background light, like near a city, you're going to do like 30-ish second exposures. If you're in a wonderful location, like on top of Mauna Loa, about 2-minute exposures seem to work out well. And then all those frames, they come out looking like this. This is a raw picture from, I think this one's taken from Mauna Loa for the pretty fast exposure. So each one of these frames that we get out, we use the raw image data, is about as much sky as your hand held at arm's length, which is coincidentally the amount of sky that the Kepler looked at during its lifetime. So we're looking at pretty big chunks of the sky. When we have really good lighting condition, this picture may contain as many as 100,000 stars, so a whole lot of them. And one of the cool things about these same open source libraries is you can do the opposite of what we did earlier. You can take a picture, and it will tell you the catalog name of all of the stars in the picture. Although if you have 100,000, it takes quite a while to figure that part out. So what we do then is we figure out the list of objects in these pictures that we want to look for planets around. So we zoom on in, we keep on zooming way in, and we end up with a tiny cropped picture like this. We call these postage stamp images because they're tiny. And there's probably a couple things you notice about this. First of all, I mentioned that stars are like point sources of light, but that's kind of smeared around a little bit. It's actually covering like 12 or 13 pixels in this image. And that's because of that atmosphere thing. Like, it keeps us alive, but it really messes with astronomy. Stars twinkle, and that makes the light kind of dance around our CCD a little bit. And fortunately, we're using cheap SLRs. They're not very many megapixels, which means those pixels are pretty big, so they don't bounce around very many of them. But that's something we have to compensate for. But if we were using a regular astronomy sensor, we would just add up all of those pixels, and it would give us a pretty good number, a pretty good photometry measurement. But we're not using regular astronomy equipment. We're using consumer cameras, which have this thing on them that make our little images, like, if you look back at that, it looks kind of like a waffle. And that waffle effect is caused by something called a Bayer filter. And a Bayer filter is how your camera can take color photos. Color photos are wonderful, like those the pictures I had earlier on that we took on of the nebula and the comet are really cool and colorful and exciting. And they're great to look at, but they are really bad for science. So we have to compensate for this also. And this one's a little more complicated, and one of the things that's more unique to this project. Because this is done with a filter, the way a filter works is it filters out the light you don't want, which is trouble for photometry because we don't know exactly how many pixels or how many photons are getting absorbed by this filter. They're gone, so we don't know. They don't make it to our sensor. So we have to do some clever trickery to compensate. So what we do is, fortunately, when you have thousands of stars in a picture, you can find your star, and it has a certain twinkle, and then you go back over the photo, and you find every other star that has an identical set of twinkling. And it turns out this happens several times in each one of these frames. And then what you can do is you can look up each one of those stars in the catalog and figure out how bright it is supposed to be. And then you can solve that equation, and you get out relative brightness between all those stars relative to what we expect those stars to be based on prior observations. In other words, we get calibration data out. You repeat this process for the same star in each one of those frames we took, the 10 to 300 frames. And we get what we call postage stamp cubes. And this is a whole bunch of those different cropped images for one star and all of the calibration data for each image. And if we take that out, we can do photometry. We can generate what's called a light curve. So here's an example of a light curve produced from a PANOPTES unit about a month ago by an intern. Did some awesome work. And so the red line actually represents what we expect the dimming to be for this planet. So this is a known exoplanet. This is actually a calibration light curve that we're using to calibrate one of the units. And the red line represents what we expect the planet transit to look like. The slope, the first slopey part is where the planet starts to partially cross the star. The flat bottom part is when the whole planet is in front of the star. And then that other slope is where it's starting to exit. And then the top flat line, which is mostly cropped off, is when the planet is either away from the star or behind it. And the blue dots represent the samples we get from the PANOPTES unit. So they're scattered about, but we have a whole bunch of them. And we get a pretty good fit for the curve. So the curve for this one came out within 0.1% of the expectation. So this particular one, transit, has about a 1.3% drop in light, and we get about that much. So it works. Yay! Oh, one thing that's cool about this picture is this light curve. This is one of the first ones we collected at non-ideal location. So this unit was actually doing observing in the LA basin, which does not have the best atmospheric conditions. I hear it's known for pollution sometimes or something. And there's some light pollution because there's some cities nearby. But it still worked great. So that was really, really wonderful for us to see. We were excited about that. So we have some telescopes up. We're doing a research project. We have data we're sharing with some scientists. We're doing our own research with it. What's happening next? In other words, how can all of you help discover new planets? Because everyone wants to discover planets, right? Otherwise, why would you be here? There are other sessions that are probably cool too. So the first thing we'd love to do is build the network, build out more, because we have a lot of low quality samples, but the more PANOPTES units we have, the more samples we have, and the better we can start looking for planets around more and more smaller planets around nearby stars and planets around more distant stars. So we'd love to have a bigger network of PANOPTES units. So this is something that's just like super excited about. Consider building one yourself. Or do you know what would be even better? Even better would be mentoring or sponsoring a school to build one. So think about somewhere you studied in the past, or maybe somewhere your kid is studying. Could they benefit from a research astronomy program? Probably. I can't think of one that couldn't. Or maybe there's a first robotics team you know that is really bored for some reason. They could slap one of these together super fast. So yeah, partner with a nearby educational institution, because one of the things we love about this is we hope that these can be used for, that the students can be involved in doing their own research and make real progress themselves. And I hear a lot of you are software developers, like myself, for some reason. I guess it's a software conference. And as all of you know, there's an unlimited number of things we want software to do. There's always more work to do, and this project's no different. We'd love help doing more software. So if you want to come and join the project and help us code on exciting problems like better scope automation, we'd love help with that. Or with the data pipeline to do the light curves. This is an area I'm a little more focused on. And until now, we've been doing most of our research, like the final processing of those light curves, just in IPython notebooks, because they're a great way to tinker around. But we're finally at the point, relatively recently, where we think it's time to start taking some of the things we have verified works on small scale and start doing it for all of the stars in all of our photos. So to do that, we need a pipeline, which will probably involve serverless and other fun buzzwords. And if none of those are too exciting to you, some of the other future projects which have not really been touched at all are things like a web or mobile interface for controlling the telescopes, because the exoplanet research is kind of like the default mission for these robotic telescopes, but the intent is for them to be general purpose instruments. So if a school builds it and maybe something interesting is happening near Jupiter, or maybe they just want a cool picture of Saturn or the Orion Nebula, we want them to be able to manually set other programs on it so that they can use it to do cool astrophotography, or they can use it to do other research we haven't thought of, like maybe looking for near-Earth objects, things like that, which would require slightly different camera settings. So we want to be able to help take this, the side quests from the primary mission. And in addition to being an exoplanet research project, this is also a really big survey. And we want to be able to share all of our photos with other scientists, which we're already doing. Right now, they're just living in a Google Cloud Storage bucket. So they're hanging out. And we've given people access to just like, here's our bucket. And they're like, there's all sorts of pictures there. How do I know what's what object? We don't yet. You have to go figure it out yourself. And one thing we'd love to build at some point is a science interface so people can be like, give me all of the pictures of this quality rating from this location of this object, to be able to search through all of our raw data and maybe classify some of our data to filter out the stuff that's like, oh, for some reason the telescope decided to operate when it was cloudy, despite the cloudiness sensor. We have some of those pictures too. So yeah, lots of software to write. And of course, I got to thank everyone who helped make the project possible. Many different organizations have helped us through grants and other kinds of support. So yeah, so if you would like to learn more about the project, go check us out at projectpanoptes.org, or check out our forum, which is kind of the most active part of discussion on the project. And if you want these slides for some reason, there's a PDF of them up on my website too. So thanks so much. And we have a few minutes left, so I'm going to do some questions. I'm going to look at the Slido thing first. And then if anyone has questions, you can throw them in there, or you can ask live. So the first question is, are you considering feeding any of your data into existing projects like Galaxy Zoo? So is that project still active? I'm not sure if Galaxy Zoo is still active. I think it is. It is? OK, it is. So we have not really considered pushing our data anywhere, because each one of the observatories, like the raw data, is about 38 gigs per night per telescope. So pushing that data around can get kind of expensive. But if someone has an interesting project and they would like to subscribe to our data, I'm sure right now, like all of our data sharing is essentially being done ad hoc on a case-by-case basis. So if anyone's interested or has somewhere you think our data should go, let us know, and we'll investigate sharing it manually with them. The next question At what rate does each new PANOPTES unit discover new planets? What is the marginal contribution of each unit? That is a great question. So we are currently in the phase, science moves a little slower than a lot of software development. The project is about 8 years old now, and we're currently in the phase where we're still refining a lot of our algorithms. So we may have the data that reveals new exoplanets, but right now we're kind of in the phase where we're focusing on further proving that our stuff will work well. So we're doing a lot of verifications of existing known exoplanets. And fortunately, there is a new space telescope that went up pretty recently called TESS, which is super exciting, especially to us because the kinds of planets we're looking for overlaps with the kinds of planets TESS is looking for, which is different than the exoplanets that Kepler was looking for. Like, we actually can't verify very many of the Kepler planets, but the TESS planets are on stars that are closer to us and have a different signal that overlaps more with us. So right now we're kind of focusing on the verification step. And as we move further forward, we'll eventually start, especially once we get that data pipeline going, some exoplanets will probably start coming out, which would be really cool. In terms of how the contributions work out, it's kind of like a sports team. No individual PANOPTES unit is probably going to discover an exoplanet. And although there are going to be some superstar units like the one at that awesome location of Mauna Loa, which gets 100,000 stars in each frame, it takes a whole team for this project to actually be successful. So, especially with the data we're getting back from like the one in the LA Basin was really promising. So it looks like a telescope almost anywhere is going to be able to contribute and make a piece of a larger discovery. There are going to be some of those points in that curve that helps us find planets, systems that maybe have several planets and stuff like that. So let's see if there are any other questions on the web thing. So no other questions on here. Does anyone have any live questions they'd like to ask? Sure. So sorry, what was that?
Is the method that you described for observing twinkles of multiple visual stars in each frame, is that used for other terrestrial telescopes?
The question is the relative photometry thing we're doing to compensate by doing the twinkles in the same frame. I'm not aware of anyone else using it right now. I'd have to go back. As far as I know, the first record of it was in the first PANOPTES paper, but I could probably go back and see if anyone cited it and has started using it. It's definitely possible someone is, but there's not really a lot of need for it unless you're using a CCD with a Bayer filter, and I think we're the only ones doing that. The question I'll kind of sweep across.
How long does a transit take? Is it several nights, or will it be able to gather all the data on a single star at one night?
So the question is, how long does a transit take? Is it a single night, or will it take several observing sessions? That's a great question. It depends a lot. There are some of the easiest ones to find that will actually transit in a single night because they're super close to their star, so they're orbiting like incredibly fast. So there are plenty of cases where we'll see a transit happen in a single night. And also if they're far away, like if the planet is far away from the star, the transit will happen for a very small portion. So the transit will often happen during an observing session. What we found from looking at our recent data is we usually get part of the transit, and we end up having to cobble together the whole transit for multiple observing sessions, which is another data processing challenge because light conditions change. But it depends on the planet. But some of them do happen very quickly. Like the Venus transit happened in only a few minutes in our solar system. Yep.
Is this like specific to the one model camera that you're using, or is any DSLR, any filter like X-trans?
So the question is it specific to the camera we're using? The general technique is not. All the fiddling we've done to make it work is specific to our camera. So there are some variations in the way the Bayer filters are laid out. So if you were to use this with a different camera, you'd have to tweak it a little bit. And there are some people who are interested in building a very similar unit with a different camera. And in that case, we're going to have to tweak the algorithm to fit there. But in the general purpose, it should work for any camera with a Bayer filter. All right, sweeping across. Any other questions? Yeah.
Yes. So you may be familiar with the Marginal Contribution telescope, or LSST, which images the entire sky every like 3 nights or something.
Mm-hmm.
How does your project complement that or do something that that can't? Is it because you're just taking more exposures, or because you're taking images at like a greater temporal resolution?
So the question is, there is a large telescope with a really, really cool mirror design that is, when the first light is really soon, if it's not already happened. LSST, which has also made some wonderful contributions to the open source software for astronomy. LSST is really cool. And the question is, how does PANOPTES fit into a world where we have these giant projects that are doing big surveys like LSST and TESS and all these other projects going on? And that's a great question. And the answer is we really complement each other. Because LSST is amazing, but it can only see a portion of the sky. So there's only one LSST. It's going to be in the southern hemisphere, or it is there. And it's dark only half the time. And sometimes it's cloudy. And like there are problems. So it can't look at the sky all the time. And one of the things we want to do with PANOPTES is we want to have a 24/7 observation of everywhere on the planet. So everywhere where there's cloudy, that PANOPTES unit's going to stay asleep during the night. But in other places, it'll be observing. So we want to get a much more continuous sample of low-quality samples from the sky. So we will have data that will be able to complement and potentially fill in holes for the time that LSST is not observing. And LSST, I actually don't know much about the kinds of things LSST is going to look at. It'll have much higher resolution than we do. So it might not even be looking at the same kinds of exoplanets, although it would certainly be capable of it. So we will be able to complement each other. And one of the cool things about the current time in astronomy is a lot of people are doing just that. There's a lot of researchers who don't actually reserve any time on a telescope. They just go out there and find existing surveys and take the data. And sometimes those surveys have embargoes, so they might have to use older data. Like if you wanted to, you could go download the Kepler data today and go look for new exoplanets. And people are starting to fuse the data from multiple sources and multiple surveys and make new discoveries, which is super exciting. So we'd love to be part of any project that does that. So yeah, I'd be super excited if someone's like, I want to mash this up with LSST data. I'm like, that's great. Here's the data. Thank you. Any other questions? Yep.
Is there a baseline area, like you mentioned New York, it's been done, or LA, close to LA, but like people who live in more urban areas, is there like a baseline of light pollution where just don't build it there, and you're not really going to be able to contribute, or is it possible to contribute, build or do one?
So is there an air quality that is light quality that's so bad? That's a good question. So I would say that it's probably not going to be too effective in a location. So like we've done shorter exposures. So what we can do is as the light pollution gets worse, we do shorter exposures, and we have some samples in places where it didn't work at all. So like if you set it up in the middle of LA, or we set one up in like basically the middle of Pasadena once, didn't work too well because it only steal about 10 stars where we were doing it. But we're targeting like magnitude 5 and lower because they're negative. No, I guess positive. So magnitude 5 and higher stars. So we don't have enough samples yet to determine where is that place where it's not going to be the right threshold. But I live in San Francisco, so that would be a really fun thing for me to do. So thank you for the inspiration. I think I might drag mine around and redo the polar alignment over and over again and find out exactly where it's going to work well and where it won't. Because that would be really useful data that we just don't have yet. All right, well, I'm officially out of time, so I'm going to wrap up. But thanks a lot for coming. Feel free to ask me questions later in the limited time left. And thanks a lot.